Hello, and welcome to this video about matrices and how to represent them as a data type in a computer. In this video, we'll investigate how to create these functions, which convert a matrix into reduced row echelon form, and to find the inverse and the determinant of a matrix. We'll see how these three functions can be wrapped up into one function and found all at once to save time. This function will be called reduce, and it will use these other two functions called pivot and row swap. So the first function we'll look at is pivot, and this is what this function does. It locates the position of this element using these parameters called I and j, which represent the row and column, and we'll start counting these from 0, so as to make it faster for the computer to read. We'll then perform a row multiplication function on the row that it is in, multiplying it by the inverse of this element, so that the element at this location is now equal to 1. Then we'll add a multiple of this row to all of the other rows in the matrix, so that all of the rest of the elements in this column are equal to 0. And so this is the end result of the pivot function. So now to write a program in JavaScript that performs the pivot operation on a matrix called A, and for the element located at R and C, R standing for row and C for column. And we'll declare these variables to be used in the function, so using them won't change global variables of the same name. We'll get the location of the element at row R and column C in the matrix array, and then we'll get the value of this element. Then we'll perform a row multiplication function on this matrix. We'll make a loop to go to all of the elements in this row of this matrix. Then we'll locate each of these elements. Then we'll divide each of these elements by the element located at R and C, so as to make the element at R and C equal to 1. Then we'll subtract a multiple of this particular row from every other row in this matrix, to make this column contain zeros in every other row. We'll firstly make a loop to go to every row in this matrix. Then we'll modify this loop so that it avoids the row that we're adding to all the other rows, so that it loops to every row except for row R. Then we'll get the value of every element at column C, the column containing the element that we've just recently made into 1, using the row mul operation. Then we'll create a second loop to loop through every column in this matrix. We'll get the location of every element in row R. Then we'll get the location of every element in the row that we're subtracting row R from, corresponding to the element in row R with the same column. And finally, we'll perform this numerical operation, which acts to subtract a multiple of this row from all the other rows in the matrix, one element at a time. The result being a matrix with the elements at RC being equal to 1, and all of the elements directly above and below it being equal to 0. So we might find a row with a 0 in the location that we want to change into a 1, and 0 has no inverse, so we'll have to do a row swap. Here's an example of a row swap between these two rows. And you can see how the numbers have been swapped in these rows. So now to make up this function, we'll declare the internal variables as usual. We'll swap rows A and B. We'll create a loop to span all of the columns of this matrix using the standard variable j. We'll get the locations for two of the elements we want to swap. They have the same column but different rows. And here's where we'll do the standard swap function using a temporary variable. So now to create the first function to get a matrix into reduced row echelon form, we'll assume that we'll get a matrix that doesn't require any row swaps and can be easily pivoted one row after the other. We'll pivot the first element, giving us this matrix. Then we'll pivot the next two elements along the diagonal. And then finally, we'll pivot the last element in the diagonal, giving us this matrix, which is in reduced row echelon form. So now to create the function to get the reduced row echelon form of a matrix, we'll create the simplest version of this function, requiring no row swaps and not needing anything special. We'll set the column variable to be 0 to start with. Then we'll make a loop for the row variable to span either all of the rows or all of the columns, whichever is smallest. This is so that this function can find the reduced row echelon form of a matrix with any shape. So now to pivot the matrix at every one of these diagonal elements. And then we'll increment the column variable inside the loop. I'm using separate variables for the rows and columns, because later on, when we make this function more complicated, we'll need them to be treated separately. Now to make this function able to calculate the inverse of a matrix and its determinant, we'll create spaces in this function so as to be able to add new lines of code. So we'll declare a new variable which will hold the value of the determinant, and we'll set this value equal to 1 and modify it further along in the function. We'll make the matrix B equal to the identity matrix, and this will be made equal to the inverse of the matrix we're reducing, if it is a square matrix and reducible. We'll modify the pivot function so that it takes the determinant value as a third parameter variable, and it will return the new value of the determinant after having pivoted the matrix. And then finally we'll return the determinant as a return value. Now to modify the pivot function, it will have an extra parameter for the determinant, and will have another internal variable to modify the determinant. Only the divide row by a scalar function can modify the determinant, and this equation tells us how it does this. We'll perform the same row operations on matrix B as on A, matrix B being our inverse matrix. This is given its own loop because the number of columns of B may be different to A, because it can find the inverse of the front end of a matrix that is an augmented matrix, with an extra column, for example. And we'll perform all the same row add operations on matrix B as on matrix A. And then we'll return the value of the determinant as a return value of the function. Now to modify the reduce function again, so that it can do row swaps when it needs to, like for example in this matrix, where the leading element is 0. We can't multiply or divide 0 by anything to make it 1, so we'll have to perform a row swap with another row, so that this matrix does have a leading non-zero element. So now we'll have to modify this reduce function to be able to perform row swaps when it needs to. We'll add a Boolean variable so that this function can tell whether it needs to perform a row swap. We'll firstly replace this for loop with a while loop, because it is less confusing, since we'll have to manipulate the indexing variables a lot more. Then we'll set the Boolean swap variable to be false or 0, and set it equal to 1 or true when the leading element is 0 and a row swap needs to be performed. We'll get the leading element and place it into a variable called L, which is short for element. Then we'll set another index variable ready to be equal to the row that we can swap with to get a leading non-zero element in this position. So we'll create a loop to look through the rest of the rows of the matrix, looking for a suitable row to swap. The next 2 or 3 rows may have 0 leading elements in them too. The leading element needs to be 0 to enter this loop. So we'll set the Boolean swap variable to be 1 or true or on. This means that we'll swap 2 rows later in the function. We'll increment the index variable, which is the row to be swapped, with row I. We'll get the next element at this position, and if it is non-zero, we'll exit the loop. and then these two rows I and K will be swapped. If two rows need to be swapped, then this Boolean variable will be set to be true, and so we'll perform the row swap. Row swaps act to multiply the determinant by -1. We'll create a loop to perform the row swap with a fourth variable called m, which will go to every element in this row, and which is a column variable. And we'll get the two locations in these rows to be swapped. Then we'll use this classic swapping algorithm using the variable called temp, standing for temporary. Matrix B will have its own loop, because it may have a different number of columns. And here we'll increment the row counting variable I, because it is a while loop. But this function still isn't complete enough, because it may have a 0 row or column, and may not reduce to become an identity matrix. So now to alter the reduce function again, so as to be able to reduce matrices that have 0 rows and 0 columns. They won't reduce down to identity matrices, and so they'll have 0 determinants, and the previous loop structures won't work for these matrices. So now we have to make this matrix reducing function able to handle matrices with 0 rows and 0 columns. We'll start off with the function that we've worked out before, that had row swapping, and adjust it. Firstly, we'll add these two Boolean variables. These tell the function whether the function has finished and whether or not it should pivot. It shouldn't pivot if it can't find a non-zero element to pivot at a certain position in the matrix, for example. So we'll set the finished variable to be false, because we'll set it to be true when there are no locations left to pivot. Since there might be 0 rows and columns, then it will be much more unpredictable when this function will finish. So we'll insert this finished Boolean variable into this while loop, so that the function can terminate when this variable is true. The exclamation mark acts as a not function, changing this variable into its opposite Boolean value. This Boolean variable looks redundant here because we're checking to see whether the counting variables have exceeded the limits of the matrix. I've decided to put it in here all the same. You can take it out if you like. We'll set the pivot Boolean variable to be true here, and then false if it finds a condition where it can't pivot, because it can't pivot when a non-zero number can't be found for a certain location. So if we've looked at all of the rows and there aren't any more rows left that have non-zero leading elements in this column, then we'll do what is in the conditional statement here. We'll turn the Boolean swap variable off so that we won't swap two rows. We won't pivot either. We'll leave this column alone. Such a 0 column will cause the determinant to be 0. And we'll insert this condition so that the function is finished if there are no more rows or columns left. We'll leave this row swap part of the function unchanged, and we'll put these two lines inside a condition statement. So we've put these two lines inside a condition statement. We'll only pivot and increment the row if the pivot variable is true. It'll be set to 0 if no non-zero element can be put into this location. We'll stay on this row and increment the column. If we're finished, we'll skip these two statements. This Boolean finished variable is a bit redundant, but we want these lines skipped if we've decided to leave the main loop. And so this will give us a very robust reducing function capable of reducing very difficult matrices. So I hope that you have found this video helpful, interesting, educational, and maybe even enjoyable. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. Feel free to share this video, and thanks a lot for watching.